The helium criticality, the strategic depletion of a critical element. According to geophysical models, among all industrially critical elements, helium is uniquely vulnerable to permanent atmospheric escape, making its terrestrial supply uniquely finite and non-renewable. This process of atmospheric bleeding has created a silent but critical dependency. As our most advanced medical and computational technologies, from MRI scanners to quantum computers, cannot function without its irreplaceable cryogenic properties. An investigation into Federal Reserve data and the element's fragile supply chain reveals not a natural shortage, but a decades-long story of economic mismanagement that has placed the future of innovation on a direct conflict with the constraints of planetary physics. The universal abundance of helium presents a stark logistical contradiction for a technologically dependent civilization. Cosmological models affirm that it is the second most common element in the known universe, forged in the primordial heat of the Big Bang and continuously synthesized in the nuclear furnaces of stars like our Sun. Yet, this cosmic prevalence bears no relation to its availability on Earth. The planet's primordial helium, present at its formation, escaped our atmosphere billions of years ago due to its low atomic mass, a fate sealed by the relatively weak pull of Earth's gravity. Consequently, the helium we access today is not a remnant of creation, but a product of terrestrial radioactivity. As documented in decades of nuclear physics research, every atom of this element is the result of alpha decay, a slow, inexorable process where heavy, unstable elements like uranium and thorium within the planet's crust shed alpha particles, which are, in essence, helium nuclei, over immense geological timescales. These newly formed atoms migrate upward through porous rock layers until they are trapped beneath impermeable formations, such as shale or salt domes, co-accumulating in the same reservoirs that contain natural gas. This direct association with fossil fuel deposits is not coincidental, but a requirement of its geology. Without the same trapping mechanism that contains methane, this fugitive element would simply diffuse into the atmosphere and be lost to space. The concentration of helium in these natural gas fields varies dramatically, with commercially viable sources being exceptionally rare, a fact well established by global geological surveys. This entire process means that Earth's supply is finite and non-renewable. The rate of radiogenic production is orders of magnitude slower than our current rate of extraction. Unlike nitrogen or oxygen, which are governed by vast and regenerative atmospheric cycles, helium is a mined resource, a finite geological inheritance. Ultimately, every atom of helium used on Earth is a non-renewable product of ancient radioactivity, mined from deep geological traps, and impossible to replace once consumed. The technological indispensability of helium stems directly from its unique position on the periodic table and the quantum mechanical laws that govern it at low temperatures. As the lightest noble gas, the van der Waals forces between its atoms are exceptionally weak, meaning it remains a gas until cooled to its boiling point of 4.2 Kelvin, a temperature colder than any other substance can reach before solidifying. This property alone makes liquid helium the most effective known refrigerant for extreme cryogenics, the final step in a cryogenic journey toward absolute zero. However, its most critical and irreplaceable characteristics emerge when it is cooled further, below the so-called lambda point of 2.17 Kelvin. At this threshold, the common isotope helium-4 undergoes a phase transition, not into a solid, but into a bizarre state of matter known as superfluid helium-II, a macroscopic quantum fluid whose properties defy classical intuition. As extensively detailed in foundational papers and modern studies in journals like Nature Physics, helium-II exhibits two primary qualities that render it essential for next-generation technology. The first is zero viscosity, allowing it to flow without any energy loss or internal friction, and enabling it to penetrate microscopic pores that would be impenetrable to any other liquid. The second, and arguably more vital property, is its extraordinarily high thermal conductivity, which is thousands of times greater than that of copper. This is not conventional heat conduction. Instead, heat propagates as a wave through the fluid, a phenomenon known as second sound, ensuring that the entire volume of liquid helium maintains a perfectly uniform temperature. It is this combination of properties that makes modern medical and scientific marvels possible. The powerful superconducting magnets at the heart of every MR-on machine, and in particle accelerators like the Large Hadron Collider, must be bathed in liquid helium to eliminate electrical resistance, a prerequisite for generating their immense magnetic fields. Furthermore, the fragile world of quantum computing is entirely dependent on the cryogenic environment that only helium can provide. The qubits that form the basis of these machines must be shielded from the slightest thermal fluctuations, which would cause them to decohere and lose their quantum information. The perfect isothermal environment created by Superfluid Helium-II, a core technology focus for companies like Oxford Instruments Nanoscience, is the foundational cryogenic medium underpinning current quantum computing systems. The quantum phenomena of superfluid helium-II, characterized by zero viscosity and near-perfect thermal conductivity, make it the primary element utilized for cooling the superconducting and quantum systems that underpin modern science and medicine. The modern helium crisis is not a failure of geology, but a direct consequence of decades of flawed economic policy and strategic short-sightedness, anchored in the history of the U.S. Federal Helium Reserve. Established by the Helium Act of 1925, the reserve was created as a strategic national asset, primarily to ensure a supply of the non-flammable lifting gas for the U.S. military's burgeoning fleet of airships, stored underground in the unique geological formation of the Cliffside gas field near Amarillo, Texas. This stockpile grew significantly during the Cold War, repurposed to support aerospace applications for NASA, including purging rocket engines and other defense-related research. For nearly 70 years, the reserve functioned as intended, a carefully managed strategic buffer against supply disruptions for critical government functions. This entire paradigm shifted with the Helium Privatization Act of 1996. Congressional reports from that era revealed that the act was framed primarily as a fiscal measure, designed to liquidate a supposedly obsolete government asset to pay off the reserve's operational debt. The legislation mandated that the reserve's entire stockpile, the time representing roughly half of the world's known inventory, be sold off on a fixed schedule by 2015. This decision, as economic analyses have since demonstrated, treated a finite, geologically irreplaceable element as a mere surplus commodity. The immediate effect was to flood the global market with cheap helium, creating an artificial price ceilings that persisted for over a decade. This prolonged period of suppressed prices had a significant and documented impact on the industry. It eliminated any economic incentive for major industrial and scientific users to invest in the complex and expensive technologies required for helium recycling and conservation. With the element priced far below its scarcity value, venting used gas into the atmosphere was significantly cheaper than capturing and reliquefying it, a practice that became standard across sectors from marine facilities to semiconductor manufacturing. Consequently, the transition from a strategic asset to a volatile commodity left the world's high-tech infrastructure strategically vulnerable. Dependent on a handful of extraction sites in nations like Qatar and Russia, and subject to the geopolitical shocks that have since defined the market. The Helium Privatization Act of 1996 effectively transformed a strategic, non-renewable element into a simple commodity, flooding the global market and dismantling the very incentives needed for its long-term conservation. The finite nature of terrestrial helium is compounded by two fundamental physical realities that ensure its constant and irreversible depletion, one operating at a planetary scale and the other at the quantum level. The first of these is the physical process of atmospheric escape. Once vented or leaked, helium atoms do not remain within the biosphere or participate in any terrestrial cycle, as extensively modeled in atmospheric physics and confirmed in studies published by outlets such as geophysical research letters. These atoms are so light that upon reaching the exosphere, the atmosphere's tenuous outer layer, they are accelerated by solar radiation and thermal energy to speeds exceeding Earth's escape velocity of 11.2 kilometers per second. Unlike the heavier molecules of nitrogen and oxygen that constitute the bulk of our atmosphere and are permanently tethered by gravity, helium atoms effectively boil off the top of the planet, bleeding into the vacuum of space. This process renders every released atom a permanent and irrecoverable loss to our world's fixed inventory. The second, and more immediate challenge, lies in preventing this escape in the first place, an engineering problem of immense complexity. At a basic level, helium's tiny atomic radius allows it to permeate solid materials and find microscopic pathways through seals and joints that would be completely impervious to larger molecules. This issue is magnified exponentially in cryogenic systems designed to handle liquid helium, and it becomes a significant engineering challenge when dealing with superfluid helium-II. At temperatures below 217 Kelvin, the element's bizarre quantum properties present the complex containment challenge. Its total lack of viscosity allows it to form a super-thin film that will creep up and over the interior surfaces of any container, defying gravity to find and escape through any potential opening. This phenomenon makes a certain rate of loss an inherent operational reality for the world's most advanced equipment, from the superconducting magnets in MR1 machines to the delicate environments required for quantum computing. The dual challenges of helium's quantum propensity to escape any container and its physical ability to permanently exit Earth's gravitational field make its depletion a persistent and inherent physical process. The collision course between our technological ambitions and the immutable laws of physics was not inevitable. It was engineered by decades of policy that treated a finite, irreplaceable element as a disposable commodity. This investigation ultimately reveals that the future of advanced medicine and quantum computing is threatened not by a geological scarcity, but by a notable lack of long-term strategic planning. The silent process of atmospheric bleeding continues, but the crisis was ignited here on the ground, through a fundamental failure to value what we were allowing to escape into the void forever. If this detailed dissection of complex technological issues is the kind of content you value, please consider supporting Tech Dissect Official by subscribing now. We leave you with a critical question for the comments. Given that past market forces clearly failed to incentivize conservation, what level of international regulation or strategic price control do you believe is now necessary to protect the world's remaining helium for essential scientific and medical applications? Thank you for your time and analysis. We will see you in the next report, where we will investigate the silent arms race in hypersonic missile technology and the physics of hypersonic propulsion and advanced ballistics.